Hi everybody, let's go ahead and get started. Just a quick announcement before we begin. The Homework 1 submissions have all been graded. The grades should be on Canvas and also in your repository. If you do not have a grade, let me know as soon as possible so that we can get that sorted out. Homework 2 is due in 2 days on Thursday. I'll be at my office all day tomorrow. So come see me if you have questions about Homework 2. And we're going to start Homework 3 on Thursday as well. So we're going to keep moving right along. Just so you guys are aware, we're getting closer to our first exam. Our first exam is going to be 2 weeks from Thursday. 2 weeks from Thursday. We will have a review session before the exam. And then one final note. You may have noticed, or not, I don't know, on the calendar, next Thursday, class is canceled. I'm actually going to be out of town. I'm going to a conference, so no class next Thursday. You can use that time to work on your homework assignment, perhaps, or study for the exam, perhaps. But no class next Thursday. So any questions about the schedule or grading or the homework assignments before we begin today? Any questions? I wanted to start today actually with our B+ tree. You can see I put the B+ tree from last class up here on the board because we did not get to do a deletion example. So I wanted to start with the deletion example before we hop into new material. Sorry, this is a little sloppy, but here's the tree that we had. It's just from the previous slide. We created this in class last Thursday, and we want to run through the deletion process for these particular values on this tree. Let's just do this together as a group, kind of a little warm-up for us today. So the first number I want to delete is 7. And the first step, the easiest step, is to find the 7 in the tree, right? Here it is. I'll take the 7 out. Do I have to do anything else right now after I take that 7 out? Yes? What do I have to do? I have 7 in the root. So 7 actually happened to be a search key. So what should we do then? What are our options? I think we actually have multiple options here. I think there's 2 different ways I could think about approaching this, right? One thing that we can do is this 7 no longer exists in the tree, so we could update it to be the 6 to indicate that it should be, 6 is the largest value in this tree. There's another option though, which is to leave it alone. Just don't touch it. Is it hurting anything? No. The fact that 7 isn't in the tree doesn't really matter. If I search for the value of 7, I'm going to follow the same path. I'm going to get to this node, and then I still have to look through these values anyway, right? I still have to search the entire node anyway to find the value that I'm looking for, and I won't find the 7, and so I'll say, all right, it's not in the tree. It's not in the tree. So actually, we can simplify this by just leaving the 7 there if we want to, and that's okay. But if you want to replace it with the 6, that's also okay. Just a little bit more work. Just a little bit more work. Any questions about that? I'm just going to leave it for now. I don't think it's going to hurt anything. All right, next I want to delete the 3. So I search, I find my 3, and I delete it. Do I have to do anything else? Do I have to do anything else? No. Yeah.
I didn't have one to move the 4 over, but...
Oh, I mean, yeah, you could consolidate, move the 4 over. Sure. But there's really no issues with taking that 3 out. All right, let's delete the 10. Question? Oh, I skipped the 4. Thank you. Let's delete the 4. I go down here and I try to delete this 4. All right. The 4 is gone. Do I have to do anything else? Do I have to do anything else? Yes. What do I have to do? What's the algorithm say we should try to do? Or let's before we talk about that, let's take a step back. Why do I have to try to do something? Because this node, it's empty, but if we want to be a little more specific, yeah, it's less than half full. That's the real measurement that we're using here. It is empty, though. That is true. That is correct. So what do I do? What do I try to do first? Yeah, go ahead. John.
Find a sibling to the same parent that has a full that's more than half full.
So I'm going to look for a sibling with the same parent. I've got two of them in this case, right? So there's actually still a question here, though. It might seem a little obvious what to do in this case. But I still have a question. Should I go to my left sibling first, or should I go to my right sibling first? Right? Or which direction should I go? It has to be an immediate sibling, right? Should I go to my left sibling first, or should I go to my right sibling first? Does it matter? Let's assume for a second that there was another value here. Maybe the 7 is still here, right? Does it matter if I go here or here first? In terms of correctness of the tree, does it matter? I don't think so. I mean, think about both possibilities. I'm either going to steal this 2, which is fine, or I'm going to steal this 6, which is also okay. Neither one of them breaks the tree. This is another situation where we just need to be consistent. We have to be consistent. So I tend to favor the left in my B+ trees. So I'm going to go to my left sibling first. Could I go to my right sibling first? Yes, I could. But I'm just always going to go to the left first, just for the sake of consistency, and see if there's a value that I can take over there. And there is. I can grab this 2 and take it. What else do I have to do? Yeah, in the back.
Did you run into any continuity issues with the left pointer from the 2 and having the 2 where the 2 used to be?
Here?
Being like kind of a less than or equal to for that left pointer?
No, that's fine.
And then moving it to the middle?
Yeah. So I moved it to the middle.
In terms of like binding the 2.
Okay.
Would you always note to go to the left versus the right?
Well, let's talk about my question. Do I have to do anything else to make this tree work? I mean, I'm not done yet. What do I need to do to make this tree work? I've grabbed the 2. There's still more work. Keys don't match, so I got to update them. Anytime I move a value from one node to the other, it's worth looking at the parent to see if I need to update these keys, and that is the case here. So I need to update these keys to reflect these new values. The 4, not a big deal, right? That the 4 is there. You could even make an argument for leaving the 4 there. It's not going to hurt anything. But this 2 is a problem. You were just mentioning that. The 2 is definitely a problem. I need to change that. What should it be? It should be a 1. Has to be. There's another issue here, right? There's another issue here with the way this B+ tree is structured now. We have this empty gap here, and we've talked about how empty gaps are a normal part of B+ tree functions because it speeds up the insertion process, right? Am I ever going to be able to put something here, though? There's nothing in between 1 and 2, so I've kind of painted myself into a corner here. I left a gap. That's an inefficiency with the B+ tree, unfortunately. Eventually, it may resolve itself if I were to delete the 2, for example, right? Then it may fix itself, or if I delete the 1, it might fix itself. But as it stands right now, there's nothing that it could ever come down the pipe that's going to fit into this position. So that's a little bit of a problem. Not one that I'm going to spend too much time worrying about, but something worth noting anyway. And so our tree is fine. This tree is okay. You could make an argument, if you wanted to, that I should change this to be a 2. I actually think that's a bad idea. Why? Yeah.
The next, if you added like a 3, then you have an issue.
Yeah. If I change this to be a 2, I'm sorry. I said one thing and did another. If I change that to be a 2 and then I want to add in a 3, for example, or even a 4, right? It would go here, which again, that's not a problem. I can put a 3 here. I can put a 4 in this node, and it's fine. It's still a totally valid B plus tree, but there's no way for me to fill this spot if I update this key. So it's just creating more inefficiencies. I guess the point that I'm trying to make is, right, leaving old search keys in your nodes a lot of times is fine. A lot of times is actually better than changing them, because it will help reduce the fragmentation that you might run into otherwise of those nodes. In some cases, you have to change them. I could not leave that 2 there. That had to be changed. But if I don't have to change it, in a lot of cases, it's in my best interest not to. Just leave it. Just leave that value. Does that make sense? Are there any questions? We had one more to do, I guess. This 2. Oh, I didn't do the 10. I keep wanting to skip numbers. All right. We delete the 10. There it goes. Okay, the 10's gone. Do I need to do anything else? Nope. We're good. And now we can delete the 2. Okay. What's going to happen? So I've deleted the 2, and we're at the same position. This node is less than half full. So first thing I try to do, look at my neighbors. Can I steal a value? I can't. There's not enough. All right, so what happens then? If I can't steal a value, what happens then? What's the next thing I'm going to try to do? Yeah. I got to merge the nodes, and I have a similar question as before. Do I take, so this node is empty, which makes the merge process a little trivial, right? But there are cases where this may not be empty. This node may not be empty, and so the question then is, do I try to merge, this way, or do I try to merge this way? And in my B plus trees, again, I always favor the left. Could I merge to the right? Sure. I just want to be consistent, so I'm always going to try to merge to the left when it's possible for me to do so. So I merge here, which really just has the effect of making this go away. Am I done? Am I done? Not quite. What else needs to happen? Where's the problem? Which node has an issue? One of these nodes is sending the wrong message right now. Which one is it? I will wait until somebody guesses. You've got a 1 in 7 chance, probably even higher if you think about it a little bit. Yes? This node right here has a problem. There's 2 search keys, but there's only 2 children, right? I have too many search keys. I don't need this many. So what do? The 1 is still good, right? This 4 is no longer necessary, so I'm going to take it out. Yeah, what's up?
Just out of curiosity, could you have also taken the 1 in this situation?
Could I have taken the 1? Yeah, I could have. Actually, that's a good point. I could have taken the 1 out and left the 4, and that would have, again, allowed me to insert values there. Yep. The key here, though, and I know I've said this a bunch of times already, is consistency. If I do it a certain way once, I need to keep doing it that way every single time. I want my algorithm to approach this process consistently. Any other questions about this example? Yeah, what's up?
For consistency, would we also have needed to move 12 to the left?
Yeah, sure. In actuality, I mean, the nodes themselves, these values, I believe, are probably just stored in an array list. a sorted array list, so I would just remove it from the list, which means I don't have to move anything. But yeah. Any other questions? What happens if I delete one more number? I want to delete one more number. What's going to happen? Notice I didn't even say which one. If I delete one more number, it doesn't matter which one. Pick a number, delete it. What's going to happen? Yeah. You're going to have to merge some internodes. You're going to have to, in other words, we're going to be removing a level from the tree. A level from the tree is going to have to go away. I mean, pick one. All right, 6 is gone. I try to borrow from here. I can't. There's nobody else for me to steal from. So I have to merge. Okay, this node's gone. But now wait a second. This guy is now less than half full because it only has one child. I have to have at least 2 children in this setup. And so it's going to try to do what? What's the first thing it's going to try to do? It's not just going to give up right away. It's going to try to stay alive. What's it going to do to try to stay alive? Yeah. Check out its own siblings, which it has to go through its parent to do that. So it's going to go to the parent and say, "Hey, I'm running out of stuff down here. Do you have any extras that you can give to me?" And the parent will go to the sibling, the other child, and say, "Hey, do you have any extras?" But in this particular case, there aren't any. This child doesn't have anything that it can give up. So it's going to say, "No, I don't have anything." So that's not going to work. And so then what happens? I tried to save this node, but I couldn't. So then what happens? Yeah. Well, this 1 is kind of gone now, right? Already. I don't need it. This is not even a tree anymore. It's a linked list, right? So I don't need that search key. The 1 and the 9 might merge. There might be numbers here, though, right? Again, less than half full. So there might be other values here if I'm using a larger degree for my nodes. So I'm going to merge these two, which has the effect of looking like this. That node just goes away. And now my tree is looking a little raggedy, right? When I merge these two, what actually ends up happening in reality is that this entire level needs to go away now. I can't sustain 2 levels of inner nodes. I don't have enough leaf nodes to make that happen. It's not sustainable. So bye-bye. That's going to go away too. We're going to be down to just the root as our sole inner node. And then I just need to reevaluate what the values should be in the root. The 1 and the 9. Again, 1 is, feels like not a great value here, right? Because it's still blocking that spot. But technically still correct. Technically still a valid B+ tree to do it that way. And so here's what it would look like in that situation. Cool. Any more questions? Any more questions? So I'm not going to do them now, but if we have time in a future class, I might. Maybe even on Thursday, if we have time. But you'll notice that for both of these slides, I ask you to repeat this example with a different degree. A degree of 4 for the inner nodes and 3 for the leaf nodes. I would very, very, very much encourage you to do those problems. I certainly could ask you to do something like that on an exam, and it will be part of your homework assignment as well, right? Your B+ tree for your homework assignment should be able to handle any degree that I tell you. Any degree that I want it to have should be able to do. So it's good to understand how this will work for other degrees, not just the setup that we've been using. Any questions before I switch over to today's material? Yes? Can we put 7, 9 as the root? Why 7? That's the original root. I mean, you certainly could, right? This is a valid B plus tree, so in that sense, sure. I agree with that. Yes, you certainly could. Again, the question is consistency. I already erased these nodes. What did I have? I had a 1 and a 7 and a 9, I believe is what I had. And typically, if I'm merging things, it's the opposite of what happens with an insertion. When I insert and I have to split a node, what happens? I push the middle value up the tree. So when I merge, what happens? The middle value is going to get lost. So I kept the 1 and the 9, the 7 went away. But technically speaking, right, the 7 would still work there. Would still be okay. Still a valid B plus tree. And I guess just one final note, I'll mention this on Thursday again too when we talk about the homework assignment, but you know, you've already noticed that there's lots of different ways that I could implement this B plus tree. On the homework assignment, I'm going to be very specific though. The tests that I give to you and that I expect you to write are going to very clearly specify, you know, do I go to the left or do I go to the right? You'll be able to run the tests and immediately know this is looking at the left. There's not going to be any ambiguity about that. But it's still good to know that those options are available to you. All right, cool. If there aren't any more questions, then let's hop into today's stuff. We're going to talk about query optimization today. So all last week we spent time talking about indexes. Today we're going to talk about queries again. This is actually very loosely related to what you're working on now with homework assignment number 2. And so what I want to look at first is what actually happens when I execute a query. What are the steps that the server takes, right, when I execute a SQL query? So I write the query in a high-level language. That's SQL. SQL is a high-level language. So I write the query, and I give it to the server. The first thing the server is going to do is it's going to parse it. We've talked about the parsing process. It creates a parse tree. You're working with parse trees on homework 2. What's the goal of parsing again? Yeah.
Generate a parse tree.
Generate a parse tree. What does it mean if I've generated a parse tree? What can I then say?
You've got all the individual pieces that translate to actual operations for your
I've got all the pieces. It means I have a valid query. It means the query is not broken, right? The query, at least, so it doesn't do things like check to see if the tables exist. That's not what parsing does. Does not know if the tables exist or not. Does not know if the columns exist or not. Doesn't care. All it knows is that the proper pieces are there and that they show up in the proper order. It's a valid query. You have stated a question that the computer can understand. That's what parsing means. If I successfully parse a query, the computer can understand your query. Doesn't mean it'll work, but the computer is understanding what you're saying and will try to execute it. So that's the next step. We're actually kind of in the next step today, the query optimizer step, which it's important to note that the query optimizer does not operate on the parse tree. It operates on the query tree. So in between this parsing phase and the optimization phase, we're taking this parse tree, we're creating a query tree out of it. Query tree dictates the execution of that query. And so once it's been optimized, we no longer call it a query tree, even though it still looks very much like a query tree. At that point, it becomes an execution plan. This is how this query is going to be executed. Think about what that means. For one query, there's actually many different query trees that I could create to represent that query, but I'm only going to select one of those to actually be executed. And hopefully the one that I select is going to be fast. That's the goal. So once I've got the execution plan, I can then turn this into actual code. We're getting lower and lower, right? We're not talking about SQL code now. We're talking about probably machine level code at this point. We're not going to talk about assembly in this class. That's a different course. And so then it gets executed on the processor, and the results get returned back to the user. So we're squarely here today in the query optimizer phase. What happens if I give you a query tree? What is the server doing to that query tree to try and make it run as fast as it possibly can? That's our goal for today. So let's talk about it. Optimization is a hard problem. It is a very difficult problem for some of the reasons that I just talked about. For one query, there can be many different possible query trees that exist. Is it possible for me to even check them all? I mean, it might be possible for me to check them all, but would it be worth it? That's sort of the follow-up question. It might take me more time to check all of the possible query trees than it would to just find a pretty good query tree and run with that. So a lot of times, we're not aiming for the optimal solution. I'm not trying to find the fastest possible query tree that I possibly can. That is not our goal. We're trying to find one that's good. We're trying to find one that's better than a crappy one, basically, right? That's what we're shooting for. It's a much lower bar, and it has to be. To search them all is just too much of a performance-intensive process. So with that in mind, I'm maybe not even going to focus on every single part of the query for optimization. There's a couple parts in particular. There's two operations in particular that I can think of that are probably going to yield the most benefit of optimization, the most improvement of optimization. Does anybody have an idea which two relational operations I'm talking about? Yeah. Project is actually not one. Any other guesses? It's not a huge number to choose from. Which relational operations do you feel like are the slowest? It's the question that I'm really getting at, right? Which ones do you feel like are probably the slowest? Yeah. Join. That's definitely one. Joins are not known for being fast. Joins are very slow. What's the other one? This feels like it might take a little bit of time. There's one that could potentially require me to scan the entire table. Yeah. An aggregate. Yeah. Actually, we could talk about optimizing aggregations, but we're not going to. There's one that's similar to aggregates that we are going to talk about instead. Yeah. Well, that has to do with aggregates, actually. Same category. We're going to focus on the select operation. The where clause could require me to compare every single row in the table, right? Those are the two operations that we're going to focus on the most. We are going to talk about projections today. Probably not about aggregates a whole lot today, but we'll talk about the other relational operations as well. But the two that we care about the most in terms of optimization are joins and select. So let's start with select. Remember, when I'm talking about the select, this is where the terminology gets confusing. When I'm talking about the select relational operation, what I'm really referring to is the where clause, right? I'm referring to the where clause. So what possible approaches are there to implementing this where clause? It might seem like a strange question, right? But I've already given you one. One way that I can implement this where clause is to visit every single row in the table, right? Every single row in the table and see if it matches the condition. What other ways are there that might speed up this process? Think about something that we've talked about recently. Very recently, yeah. Could we sort? So sorting is a good idea because that's going to make it easier to find values that we care about in a lot of cases, right? However, sorting itself takes time. So while I do like the idea of searching a sorted column or set of columns, could have its own problems. Yeah. I'm sorry? Yeah. An index. Yeah. If there's an index on the column, in the where clause, that's going to make my life a lot easier. I no longer have to scan every single row. What do I do instead? I crank it through the index. So if the column that I'm searching for has a B plus tree index on it, right? A multi-level B plus tree index. Excuse me. If I'm doing a simple equality, that's easy. Take the value that I'm searching for an equality for, plug it into the tree. Remember, this is fast. This is very fast for searching. Find the node where it's at, and boom. I no longer have to scan every single row in that table. I just have to use a search tree. If I'm doing something, more broad, like a greater than statement, for example, it's still possible, right? Do a search, and then take all of the nodes to the right of the one that you've found. Remember, these are linked together. I don't often draw them, but these are linked together. So I can do a search and then just grab all the nodes farther down the list, and I've still chopped off a large chunk of stuff that I don't need to search for, right? So indexing is a big key here, and if I have more complex search conditions, like compound search conditions that use ands and ors and things like that, indexing can still help me. In fact, I haven't talked about it before now. We haven't even really seen any examples of this. But I can make an index that is indexing not just one column, but multiple columns. It's entirely possible for me to do. Think about how that would be done. I just need to have a way of determining the order, how those two columns are ordered in relation to each other. So I could, I don't know, maybe try concatenating the values together somehow, right? Or something along those lines to help me sort those values. So basically, the point I'm trying to make here is the more columns in my where clause that are indexed, the better that where clause is going to be performance-wise. Seems like a very obvious statement to make. That's what indexes are for, but it's worth keeping that in mind. So we can define a value called selectivity. Of all the rows in a table, right, how many of them are going to match this search criteria that I'm looking for? How many of them? We express this as a percentage. So selectivity is typically a value between 0 and 1. Can I know this value? So it's asking if I can compute this value exactly. If I'm looking at a query and it has a where clause in it, can I tell you the selectivity of that where clause? Can I just look at that where clause and be like, oh, the number of rows that match this particular criteria is going to be 60%. Can I say that? Is there anything that I have at my disposal that can make me say that? It's not possible. I haven't run the query yet. I can't know how many rows are going to match the criteria until I actually go through and run the query. But we can use that to our advantage. A lot of times I'm going to be running the same query multiple times, or even similar queries multiple times. So the first time I run a query, if it has a where clause, I'll see how many rows match and I'll record that selectivity. I will record that selectivity and save it for later, so that if the same query comes back later, or a very similar query comes back later with a similar where clause, I then actually have an idea. All right, I expect this to match about 60% of the rows in the table. How does that help us? How does knowing that selectivity help us? What's the advantage? Yeah.
If there's a more efficient way to optimize a query with high selectivity, it knows to choose that method, and if versus one that's better for low selectivity.
I think you're getting at the point here. I mean, I can start categorizing the where clauses by low selectivity and high selectivity, or I might have a compound where clause that's got two conditions separated by an and, right? And then the question is, well, which one do I do first? And if I want to use some criteria to determine which side I'm going to do first. Selectivity is a great criteria for that. Which one am I going to do first if I have the option? The low selectivity one, right? I'm going to filter out as much data as I possibly can right away, because that's going to make the second one even faster. There's going to be fewer rows for the second one to have to consider. Low selectivity queries in general are going to be better for performance. The more data I can eliminate, the faster my future operations are going to be, because they're going to have less data to have to consider. So I'm going to prefer low selectivity operations when possible. We'll see this pop up again later, towards the end of class. Any questions so far? All right, let's talk about joins then. We're going to talk about joins quite a bit. It may or may not surprise you to learn that there's more than one way to perform a join. The way that I've talked about joins in the past when I introduced them is through a nested loop join. So I have one loop that goes through one table and another loop that goes through the other table, right? It's if I asked you to write a Cartesian product function, you would do it this way. One loop to go through and a nested loop to go through the other one. And I just check every single possible combination. Does it match, does it match, does it match, does it match, does it match. It's brute forcing it. I'm brute forcing it. It's slow. It's very slow. It's always going to be n squared, right? At least. At least. So it works. It gets the job done. But there are better ways to do it. If I can get rid of even one of those loops, it's going to vastly improve the performance of my joins. And I can get rid of one of those loops. I can do a single loop join. How? What would I need to get rid of one of those loops? What could make this join process a lot faster, a lot more straightforward? Something that we've been talking about very recently. We talked about it just a few minutes ago, as a matter of fact. Rhymes with Windex. That's right. If one of the columns that I'm joining across is indexed, that allows me to eliminate one of the loops. I loop through whatever column is not indexed, and then I pass those values into the index. And it will very quickly tell me if it's a match or not. Right? So getting rid of one of those loops is going to speed up the process a lot. That's why when it comes to deciding which columns I'm going to index, foreign keys are almost always going to have an index on them for this reason. Almost always. To try and simplify this join process. That's not the only way to do it. The next one on our list is a sort merge join. So if the columns that I'm joining, that I'm checking in my join condition are sorted, I think you can see that the process would be a lot faster, right? I no longer have to scan both through the entire thing. I can just move the cursors depending on how the values are, greater than, less than, to each other. It looks a lot like merge sort almost, right? The very last step of merge sort, combining those two values, two sets together. The problem with this one is that it requires the columns to be in sorted order. So there is one common way that we see columns in sorted order. What's something that we've talked about that requires columns to be in sorted order? I'm sorry? The primary index. Yeah, the primary index sorts the entire table by a particular column, usually the primary key. That's actually very convenient for us because if we're going to be doing joins, we're probably going to be using the primary key of a table to perform the join, since that's what defines the relationship. The problem is with the foreign keys, right? Or whatever the other column is, it requires both of them to be sorted in order for this to work. So the foreign key column in another table probably is not going to be sorted. So I have two options. I could sort it before I do the join, right? But then I run into that same problem that I talked about before where sorting takes time. Is it worth the time to sort that column before doing the join? That's not always a black and white issue, right? Sometimes the answer might be yes, sometimes no. Ideally, though, this case works the best when both columns are already sorted. In fact, if both columns, I'm sorry, I lost my train of thought there. My brain just stopped working. I've been very sick the last few days. All right, let's talk about the last one, partition hash. This is maybe the most elaborate scheme of the 4 that's up here. The first step is to partition the data. And to partition the data, we actually run one of the columns through a hash function. So I'm going to hash everything into buckets. And then to perform the join, what do? I go through the second table and I start hashing those values. And if I have a collision, right, boom, I know that I've found a match and I can perform the join. If I don't have a collision when I try to hash those values, then there's no match and I can just skip that one and move on with my day. Hashing is very fast, right? Constant time. That's what makes this process attractive. It's not a nested loop. I'm looping through one table and then the other table separately. So I have 2 loops, but they're not nested. That's where the performance improvement comes from with this particular situation. The problem with this is that hash table. Hash tables take up space. If my hash table is too big, it's not going to fit in memory. I'm going to have to start putting it on disk. And if I have to start making extra trips to disk, that's not a very fast operation. Going to disk is slow. It's slower than memory anyway. And so it may kill any optimization, any performance improvement that I would expect to gain. So for partition hash to be a viable option, it typically requires that one of the 2 tables that I'm joining be small enough to fit into memory when I hash it. I want that hash table to fit entirely into memory. If it's too big and it starts spilling over into disk, then it's not worth it. It becomes not worth it anymore. So those are the 4 kinds of joins that are available. And when, if the server comes across a query that has a join in it, it's going to start evaluating criteria to try and pick which one is the most appropriate, right? Which one do you think that the server wants to do? Which one is the fastest? What's the ideal case for a join? Which one do I really want to do? Any ideas? Which of the 4? We can probably rule out nested loop. That one sucks. Which of the other 3 is going to be the fastest? Partition hash or sort merge are the 2 that I heard. Sort merge is the fastest one, but it's also one of the least common because finding columns that are already sorted, having both columns already sorted, is a pretty rare event. If it happens, though, you hit the jackpot. That join's going to go very quickly. Partition hash is more common, but it does require small tables, so that is a barrier to running that one. But still very good performance if you can pull it off. Single loop is not the fastest on the list, or probably not even the second fastest on the list, but it is one of the most common ways of performing joins because indexes are pretty cheap. Indexes are pretty cheap to do and pretty easy. So if you are very smart about how you index your database, you can almost always ensure that your joins are going to do the single loop or better. The nested loop, of course, is the worst case scenario. It will always work. It will always work. There's nothing stopping you from using a nested loop to perform your joins, but it's going to be slow. Are there any questions about that? Yes? What's the difference between index and the primary key? So the primary key, what's the purpose of a primary key? To uniquely identify every single row, every single tuple in the table. That's what the primary key is for. The purpose of an index is to provide a secondary access point to your data. So I can index any column that I want, including the primary key, but any column that I want. So, I mean, not all of my columns are going to be able to uniquely identify every row, right? So an index can still accommodate those columns. We talked about the different kinds of indexes a week ago, last Thursday. The primary key is often used as an index value, but other columns are too. Yeah? What if the index is too big to fit into memory? Yeah, sure. Then, I mean, it's going to slow you down. Absolutely. Notice, though, that the only ones where the only join that I care about memory size or not is the last one, partition hash. That's the only one where I really am trying to fit a data structure, make sure the data structure fits into memory to perform the optimization. For a single loop that uses an index, it's true that the entire index probably will not all fit into memory. But that's okay. That's not a condition of that. It's still going to be faster than doing the nested loop. In fact, we'll take a look at a nested loop example, I think on the very next slide. Where does the index live? How do I pull out pieces of my index? This is review, but we're on the topic, so. How is an index stored on the database? Heap files. Heap files. What are the pages? One page in my heap file represents what of my index? Think about a B+ tree. One page is, yeah.
Either a leaf or a
Inner. It's a node. Either a leaf node or an inner node. One page, one node. Yep, that's review, I know. Not today's topic, but still good to reinforce those concepts. Let's talk about nested loop joins real quick. A few weeks back, or whenever I first introduced you to the concept of a join, I asked you a question about the order that the join takes place. In fact, somebody was asking about this on Piazza last night as well. My question is, does it matter the order of the tables that the tables show up in a join? If I want to join two tables together, right? I could say A join B, or I could say B join A. And my question is, does it matter? Does it matter which order I do it? Functionally, the answer is no. I'll get the same result no matter what. But let's talk about performance. Does it matter from a performance perspective? What if we now understand that saying A join B means that A is going to be in the outer loop and B is going to be in the inner loop, right? And then B join A would be B is in the outer loop and A is on the inner loop. Now does it make a difference? Now do I have a preference which one I want? I see some people shaking their head no. Let's do some math. I have an example here. I've got one table with 10 pages of data and another table with 2,000 pages of data. The question is, how many page accesses do I need if I'm doing this with a nested loop? I've got two different versions, right? Got two different versions, all right? Let's do them both. I've got 4 10 pages and then 4 2,000 pages. And then I've got 4 2,000 pages on the outside. And then I've got 4 10 pages on the inner loop. So let's do the math. This loop's going to run exactly 10 times. That's 10 page accesses, right? This loop, I've got 2,000 times 10. So the total number of page accesses that I have is 10 plus 2,000 times 10. So that's 20,010 page accesses for this one. All right, let's do the same math over here. This loop's going to run 2,000 times. This loop's only going to run 10 times, but that's going to be another 2,000 times. So now I've got 2,000 plus 2,000 times 10. This is 20,000, so now I'm at 22,000. This one requires more page accesses. Think about it for a second. This inner loop is always going to require the same number of page accesses, just this value times this value, every single time. So it all has to do with this outer loop. Whichever the smaller one is in the outer loop is going to save me page accesses. So with that in mind, the answer is yes, the order does matter. The order that I join the tables does matter in terms of performance. They'll both work. They'll both get me the same results. They're both correct. But this one is faster. So for a little bit of perspective on this, a little bit of a history lesson on this, right? In the past, you used to have to think about this when you were writing joins and say, all right, this table is smaller than this table, so I'm going to put it first. I'll put the next largest table and then the next largest table. You used to have to put some thought into it. Today, that's not true. Today, the optimizer is smart enough to do that for you. So in practice, you don't have to worry about it. Just write your join. Just get it to work, and the optimizer will flip the tables if it deems that it's necessary to do so. It will manipulate those tables. In fact, that's a good point too, right? I don't get to choose how these tables are joined together at all. As a programmer, as somebody writing SQL, I don't get to pick that it's a sorted join. I don't get to pick that it's a single loop join. Well, kind of, right? I get to create indexes and encourage more single loop joins. That's how I have control over the process. But I can't tell the server, do this join in a partition hash, right? I can't do that. The server is going to look at my query, determine if a partition hash can be done, and do it if it's possible. It's all being done for me. Same thing with this. The order does matter, but the server is looking at that and taking care of it for me. We don't have to worry about that anymore. Any questions? All right. How many records from each table do we expect to match the join condition? This is the selection factor. It's very similar to the selectivity that we talked about with the where clause, with the select operation. If I have an idea of how many records from each table I expect to match, how does this help me? How can this help me optimize my query? Yeah.
Similar to the last one, you'll want to pick the one that has the small selection factor first.
I'll do the smallest selection factor first, and then the larger one if I need to. Of the join types that I have, which one does this help me with the most? It's maybe not quite intuitive. The one that it helps with the most is actually probably the single loop, the one where I have an index. Remember, I'm only using the index for one of the tables in this setup, and I'm looping through the other table. So the question is, well, what if they both have indexes available? Which one goes in the loop, and which one do I use the index for? Well, I'm going to use the one in the loop that has what? Lower selectivity, so that loop I can keep as short as possible, probably. As just one example. Excuse me. And again, when I'm looking at a query, I actually don't know what that selection factor is going to be. I have to run that query first, count how many rows match, and then I know the selection factor, which I will store for later. Remember that for later so that I can use it on future queries. Where does that data get stored? Where do I store the selectivity data? Where do I store this join selection factor? Where am I going to put that? I'm sorry? The heap file? Yeah, but where specifically? Which part of the database does that belong in? If you look at your homework assignment, right? Of all the different parts of your homework assignment, which one makes the most sense to store this kind of information? Not a visitor. What kind of information is this? Is it data? It's metadata. So where does the metadata go? Description? Where do I keep the descriptions? Descriptions are also metadata. Where do I keep those? How do I look up the description of a table? Where do I go? Rhymes with catalog? I don't know. That's a tough one. The catalog stores our metadata. The catalog stores all of our metadata. MySQL has a catalog. I don't think it's called catalog. It's called, I'm drawing a blank. Maybe it is called a catalog, now that I think about it. But you can examine the metadata of any database. It's in there. You can take a peek. The catalog is what's doing that for our database. It tracks all the metadata. So if I wanted to store these values, I would make some entry in my catalog to store them for me. All right. Okay, let's get down to the actual act of optimization. I've got a query tree. I want to optimize it. That's where we're at. I want to optimize the query tree. I want to make it as fast as possible. What are the steps that I can take? Again, remember, I'm not making any claims about being able to find the most optimal query tree. That's not what I'm trying to do. I'm just trying to find a query tree that's good or better than the one that I started with. So we've got a set of heuristics that we're going to run. We're not going to find the fastest version. We're just going to find a version that's better than the one that we started with. If we apply these heuristics, we know that it's only going to improve the query tree. It will never make it worse. That's the idea. But we may not end up with the quote-unquote optimal solution. So in order to, we're just going to run down a list of heuristics for each of the different relational operations. And then what I've got is an algorithm that you can use that applies these heuristics to a query tree, and we'll do it on an actual example. So here are the heuristics. If I have a query tree and I've got a bunch of select operations, conjunctive select operations, right? Meaning that I've got a where clause with an and in it, right? This condition, and this condition, and this condition, and this condition. This heuristic says I can break those apart and cascade them, do them one after the other. Does that make sense? I don't have to treat those conjunctives as one big giant select operation. I can treat it as a series of smaller select operations. That's what the first heuristic is telling us. These operations are also commutative, which means that I can switch the order of them, and it'll still get me to the same place. Okay? Projections. If I have a bunch of projections that I need to perform, if I have a bunch of projections that I'm performing one after the other, this heuristic says that it's pretty much irrelevant. Why? I'm doing a bunch of projections, doing a bunch of projections, doing a bunch of projections. Which one really matters? If I'm going to run 10 projections in a row, which one really matters? Which one's going to have the biggest impact? Any ideas? Think about what it means to do a projection. I'm specifying what columns I want to keep. So I might have a list of projections that says, keep these 3 columns. And then the next projection would say, keep these 2 columns. And the next projection would say, no, keep these 4 columns. And the next one would say, keep this single column. Which one matters the most? Yeah. That's right. The last one. If I'm running a bunch of projections in a row, the last one is the only one that matters. It's the only one that counts. Because it's basically going to erase all of the other projections that came before it. Right? I'm saying keep this column. So any columns that were there before, doesn't matter. Whatever the last projection says is what sticks. In some cases, they can be commuted with a select operation. So I can take a projection and a selection, and I can swap the order. When? When is that possible? There's there's a particular condition that has to be true in order for me to be able to swap the order of those things. What needs to be true? Let's think about it this way. Maybe I've got a where clause that says where A equals 7, right? Doesn't matter. And now I've got a projection that says, you know, select B. Can I swap the order that these two things happen and get the same result out? Can I do this part first and then this? Will that work? I see people nodding their heads. This says keep column B, throw away all of the other columns. This says try to match column A to 7. So if I say keep column B, throw away all the other columns, how can I match column A to be 7? I just threw it out. I just tossed it. So I cannot switch these operations. I cannot switch the order that I do these operations in. I have to do this one first and then do the projection, because this projection is going to remove the column that I'm trying to use here. Does that make sense? So if I want to be able to switch the order, they have to be the same. I have to be projecting the columns that I'm selecting. The columns of my where clause have to show up in my projection. If that's true, then I can swap the order. And it may be beneficial for me to do so, right? It may be to my advantage to do that. A few more of these. Joins. So I can swap the order of a join with a selection if the selection only affects one side of the join, which makes sense, right? If that selection affects both sides of the join, then I have to do the join first and then perform the selection. Otherwise, the columns won't be available to me. Similar idea is true with the projection. If I have a projection and I have a join, I can swap the order of those two things as long as all of the projected columns are part of the tables being joined. If I'm projecting columns that aren't part of the tables being joined, it's going to remove the columns that I'm going to need to perform that join, that I expect to see in the result of that join. The set operations we're not going to see actually very much at all, but I included them mostly just for completion. So I'm not going to spend a ton of time talking about these particular heuristics, but we actually already mentioned this when I talked about relational operations a couple weeks back, how union and intersection are commutative, and then union, intersection, and join are associative. They all are commutative with select. Project and union are commutative with union. You don't see unions very much. They're just not very common operations with SQL queries, so I'm not going to delve too much time into it. This last one, though, is one that we will see. A Cartesian product and a selection is a join, right? We talked about that in class a couple weeks back when we did relational statements. So think about what that means. If I see those two distinct pieces in a tree, I can actually combine them together, form a join. I think I've got, all right. So these are just rules. These are things that we can do to our tree. But how do we apply them? That's what this is for. This is an algorithm. This is a heuristic, a set of steps that we're going to apply to a query tree to try and optimize it. Step 1 says we're going to break up any conjunctive selects. So what that means is if I have any compound conditions, do this, and do this, and do this, and do this, I'm going to break them up into smaller pieces so that I can move them around the tree. It's going to make it easier for me to move those smaller pieces around the tree. Okay? Once I've broken them up, I'm going to take those select operations and I'm going to try to push them as far down the tree as I possibly can. Why? What's the benefit? How do I evaluate a query tree? I start at the bottom and I work my way up. So when I say that I'm going to push the select operations as far down the tree as possible, what does that really mean? It means I want to do them as soon as I possibly can. Why? What's the advantage? Yeah. Narrows not the amount of columns, but the amount of rows that I have to work with. The select operation is rows. Projection is columns. But yes, that's right. I'm reducing the number of rows that I have to work with as soon as possible. I'm trying to get rid of as much extra data as I can, as fast as I can. That's going to speed up any future operations that I need to perform. If I've got multiple tables involved, if I'm doing a join, for example, any tables that have selections on them, I'm going to move those as far down the tree as I possibly can. Again, think about why. If I have multiple tables, I'm going to be doing a join at some point to join those tables together. I want to join tables that are as small as possible. So to reduce the size of those tables as much as possible, I'm going to do the ones with select conditions first, because that'll reduce their size. That'll make the future joins even faster. We're going to combine Cartesian products with selects when applicable to turn them into joins. That's a pretty obvious step. And then the last step is to move projections as far down the tree as possible. Notice projections being the last step shows you that projections, while still useful in terms of optimization, are not going to be where the bulk of the optimization comes from. But the general rule here is I cannot project a column off. I can't remove a column if I need that column farther up the tree. Or another way of thinking about it is, as soon as I've used the column and I determine that I don't need to use it anymore, get that column out of there. Project it off. Get it off the query tree. Let's do an example. Let's walk through an example. This is actually taken from the textbook. So here's my query. I've got 3 tables. This X, remember, right? That's a Cartesian product. That's not a join. It's a Cartesian product. This guy here is a big old selection statement, and then I've got a projection here as well on last name. So we're going to follow this heuristic step by step. Step 1 says to break up conjunctive selects. Step 2 says, all right, then take those selects and move them as far down the tree as we possibly can. So if I think about those 2 steps, I'm going to take this one big giant select statement, and I'm going to break it up into, what is that, 1, 2, 3, 4 separate select statements. 4 separate select statements. I'm then going to take those 4 separate select statements and try to push them as far down the tree as I possibly can. This requires us to think about, what tables these statements apply to, right? For example, if I look at this one, this is employee social security number equals social security number. So employee social security number is going to come from the employees table. Social security number is probably coming from works on. This is actually a join condition, right? So I cannot move it past this Cartesian product. I can't push it any farther down because this Cartesian product needs, we need both of these columns, right, to perform this selection. And I don't have both of those columns together until after this Cartesian product is finished. But if I look at a different one like P name, project name equals Aquarius, that only depends on one table. Project name only depends on this table. So this project name, I can push it all the way down so that it's just above the project table. Birth date, I'm assuming that's employee birth date, right? Only depends on the employees table. So I'm going to take this birth date, I'm going to push it all the way down so it's just above this employee table. I'm going to move it as far down the tree as I can. If my selection condition involves things from multiple tables, I have to do it after the Cartesian product. If it involves values from just one table, I can do it before the Cartesian product, and I want to. I want to. So here's what it might look like once we've completed steps 1 and 2. I broke the selections into pieces, and I've moved them as far down the tree as I possibly can. Notice that I still have one up here at the top, right? P number equals P number, because this comes from the project table, and this one comes from the works on table. All right, what's the next step? The next step says, when performing operations on multiple tables, move relations with select restrictions as far down the tree as possible. What effect does that have on this tree? Am I going to be reordering my tables? What do we think? There's only 3 tables, and actually 2 of them are on the same level. Employee and works on are as far down as they can go. So the question is, can I move the project table lower or not? That's the question that I have. Can I move the project table lower or not? Do we have any ideas? I keep saying project. It's project. I don't know. It's a subtle difference. It's bothering me though. Can I move the project table lower in the tree or not? I mean, the answer is actually always yes, I could, but I guess the better question is, should I? Will it make the tree better? And the answer is yes, actually. It will. It will make the tree better. I swapped it with the employee table, which seems odd because the employee table had a select operation on it. So what makes this select operation better than this select operation? Yeah. The equality versus the greater than. I expect this equality to be a lot more selective than the greater than. I expect that equality to return a result with much fewer rows than something with a greater than. So I want to do that one first. I want to move that one farther down the tree. Again, I'm trying to get as many rows out of there as soon as I possibly can. That's a tricky step. It trips a lot of people up, but it's an important one. All right, let's back up and take a look. Next thing it says, combine Cartesian products with selects. This is probably the easiest part. So I see a couple of these selections, right? This comes from this table and this comes from this table. There's a Cartesian product here. So what we're going to do is we're just going to merge those two together. It becomes a join. Same thing up here. These are going to become a join. So if I look at the results, here we go. These have become joins now, which simplifies the tree. And the last step has to do with projections. We're going to move projections as far down the tree as we possibly can. So I look at this, and I actually just see one projection on last name. One projection on last name. So last name is, I'm assuming, from the employee table. But what this rule is really saying, I think, if I could rephrase it a little bit, would be, as soon as I know that I'm done with particular columns, I'm going to get them out of there. I'm going to project them off. So I know that by the time I'm done, the only column that I want is the last name column. That is the only column that I want to see at the very end. At the very end. So I can come down here and look at this, for example. Excuse me. If I look at this project, for example, I have this selection here on the P name column. But as soon as I'm done with that, I can actually do a projection and get that column out of there. In fact, the only column that I have to keep from this project table is what? P number, since I use it in the join. Since I use it in the join. So what I would do then, what I would expect to see on this tree, is a projection after this selection on P number. It's going to get rid of all of the columns except for project number because I don't need them. I don't need them anymore after that point. And you can think of a similar process here, right? For the works on table, I can project off all of the columns except for project number, again, because that's the only one that I actually need. Yes?
There's one thing. Won't you still need ES?
Oh, I'm sorry, you're right. You are correct. So I need project number and social security number, I think. Thank you. You're correct. So I have to keep both of those columns around. For employee, I need the birthday column to do this, but as soon as I'm done with that, I can get rid of all of the columns except for social security number and last name. So I'll project those off as soon as I possibly can. And so the result, the final tree, might look something like this. Here's project. You can see as soon as the selection is done, I'm going to project off everything except for the column that I need to do the join. This works on table. I'm going to project off every column except for the ones that I need for the 2 joins that it's a part of. Employees table, I'm going to project off everything that I need except for the column that I want at the very end and what I need for the join. You'll notice that even after I do this first join, all right, then I project off the project number column because I don't need it anymore. I did the join. I used this project number column. It's done. I don't need it anymore, so I'm going to get rid of it. I'm just going to keep the column that I need for the next join. I'm going to project everything off as soon as possible. So that last rule actually has the effect of inserting a lot more projections into the tree, is basically what ends up coming down to. Are there any questions? We're actually out of time. All right, homework 3 is going to come out on Thursday. Homework 2 is due on Thursday. So come see me in office hours tomorrow if you have questions about those things, and I will see you in class in a couple days.